You're listening to this right now through the cloud, right? But what if I told you the cloud isn't, floating in the sky at all?
Right, it's actually buried in the wall.
Exactly. It's wrapped in Kevlar and pulsing with literal lasers. So welcome to the deep dive. Our mission today is to look at the invisible physical infrastructure that actually makes your digital life possible.
And we're doing that using just one single piece of gear, right?
Yeah, exactly. A product page from HDTV Supply for the Avenview FO-MMD-SC-SC-100.
Which is a 330-foot duplex fiber optic patch cable.
Right, and spending like $348 on a single cable might sound like buying a completely over-engineered extension cord.
It really does.
But when you dive into the specs, you realize the crazy level of precision happening just to get, say, a YouTube video to your phone. Okay, let's unpack this.
Let's do it.
So the spec sheet calls it a 50125 multimode duplex cable. Now, I usually think of data like traffic, right? A basic simplex cable is, a one-way dirt road. But this duplex multimode cable is a two-way superhighway. But how exactly does multimode handle all that traffic without crashing?
Well, that's where we look at those numbers, the 50125. They refer to the physical dimensions of the glass fiber in microns. So the 50 is the core, which is this microscopic laser-optimized glass center.
Okay, a glass center.
Yeah, and to build on your highway analogy, multimode doesn't just shoot one laser straight down the middle. It actually bounces several different colored light beams off the walls of that core at different angles simultaneously.
Oh, wow, all at once.
Exactly. They all zigzag down the same tube without colliding.
Got it. So the light is literally bouncing down the pipe. But wait, if it's constantly hitting the walls, how does the signal not just bleed out the sides and fade away?
Right. So that's the 125 part of the spec. That is the cladding wrapping the core, measuring 125 microns. And it acts like a perfect mirror,
Right.
basically forcing the light to keep bouncing forward rather than escaping. Because of that wider 50-micron core and the highly reflective cladding, this specific design can effortlessly push 10 gigabit speeds across hundreds of feet.
That is insane. But, a sprawling multi-lane superhighway is totally useless if you can't build an off-ramp, right? You eventually have to plug this Lightspeed glass tube into a metal server rack.
I do, yeah.
I'm looking at these SC connectors on the ends, and it's just a square push-pull block. Honestly, my home AV setups always use those twist-on plugs so they don't accidentally get yanked out. Why overcomplicate the plug? Why not just use those standard twist-style ST connectors?
What's fascinating here is that the physical environment completely dictates the engineering. You really have to picture high-density server environments or, like, vast sports bar TV matrix systems.
Oh, where everything is jammed together.
Exactly. In those incredibly tight spaces, you might have literally hundreds of ports packed side by side. You do not have the room to get your fingers or a tool around a connector to twist it into place.
Wait, really? So it's not about making a fundamentally better connection, it's strictly a spatial limitation. You physically just can't fit your hand in there to twist it.
Yeah, exactly. The SE connector solves this with a snap-in, push-pull mechanism. You just push until it clicks. But inside that plastic housing is a highly precise 2.5 millimeter ceramic ferrule.
The ceramic ferrule.
Right. The ceramic guarantees the glass fibers align perfectly. It's rated for 1,000 mating cycles with an insertion loss of just 0.25 decibels.
Wait, 0.25 decibels, what does that actually mean in practice?
So to put that in perspective, it means even after clicking that connector in and out 1,000 times, the light passing through the junction barely degrades at all.
Wow.
It's practically as perfect as a permanently spliced wire.
That's incredible. So what does this all mean for the real world? Like, who is actually dropping this kind of money on a push-pull optical cord?
Well, this cable features an OFNR jacket, which stands for Optical Fiber Non-Conductive Riser. Essentially, it complies with strict building codes for running vertically between floors in commercial spaces, without being a fire hazard.
Ah, so this isn't for a home theater?
Not at all. It's built for military applications or sprawling citywide and global webs, what telecommunications call metropolitan and wide area networks, so MAN and WAN.
Right. Places where uptime is absolutely non-negotiable. And the specs also mention it comes in a zip cord style. Does that play directly into those sprawling commercial installations?
It does, yeah. A zip cord design means the two independent fibers, so the transmit and receive lines, are joined down the middle but can be peeled apart.
Literally like a zipper.
Literally like a zipper. So when an installation team is running hundreds of feet of cable through a ceiling or a riser, that quick physical separation saves significant labor time. And less labor means lower installation costs.
Right. That makes total sense. It really reframes how you think about getting information from point A to point B. I mean, every hyperspecific choice, from the reflective 125 micron cladding to the push-pull ceramic latches, is crucial for maintaining the lightning-fast data environments we rely on every single day.
Yeah, we definitely tend to take that invisible infrastructure completely for granted, right up until the moment a connection drops.
Oh, absolutely. So we'll leave you with this final thought to ponder. We love to talk about living in a wireless world, floating effortlessly in the cloud. But consider that every single piece of data in our supposedly wireless world ultimately relies on physical zip cords.
Yeah, that's the crazy part.
They are pulsing with literal light from highly specialized LED and VCSL lasers, which are basically ultra-efficient, vertically emitting light sources. The cloud isn't in the sky at all. It's incredibly grounded in physical precision engineering.